Um, Hello, everyone. Welcome to the very first online event for the Oxford University Aeronautical Society, or AerOx. I'm just going to introduce AerOx a little bit and then talk about Anna and the talk, and then we might move on to the talk directly, so please bear with me. And we're just going to stall a bit of time for more people to join us. So first, AerOx. AerOx is the Oxford University Aeronautical Society, so we're not-for-profit. And our aim is to basically promote and develop knowledge surrounding aerospace and aviation in general, usually through like high-profile speaker events at this university. And we are currently also open for applications on committees. So if you're a university student interested in space in general and want to work with us to organize events, please feel free to email. We have all the information on the website. And if you have any questions for Anna, during this talk, please submit them to the YouTube channel thread, and we'll try to answer them at the end. Or you can also tweet us at @AerOx_space. So please be sure to ask your questions. We're very much open to participation from the audience. Now, a bit about Anna, who's here with us, Dr. Anna Horleston. So Anna is the Planetary Seismologist, currently working as part of the MarsQuake Service for NASA's InSight mission to Mars, which we're going to talk a lot about. She's based in Bristol. With a background in astrophysics and seismology, Anna has spent over 15 years deploying seismometers all over the Earth to study phenomena ranging from landslides and fracking to subduction zones, volcanoes, and the structure of the deep Earth. And now she focuses on detecting Marsquakes and determining the structure of Mars itself, which we're going to focus on a lot. So the talk, and obviously she will expand on this, but this is about NASA's InSight lander, which is the first dedicated geophysics mission to Mars, carrying a suite of geophysical instrumentation. And the aim of InSight is to determine the internal structure of the red planet, and maybe shed light a bit on its terrestrial planetary formation in general. And InSight's primary instrument is a seismometer. And today, Anna will be talking about the mission. We'll be briefly showcasing the sound of the wind of Mars, which I'm very excited about. The seismic signals that we see and what it tells us about Mars. So Mars, oh my God, Mars. Hi, Mars. Anna, before we delve into the actual talk, I'd just like to briefly touch upon your background in science communication, because I'm very interested in that as well. And I was wondering if, with all your work with the Royal Society and the at Bristol Science Center, if you guys want to check that out, how do you think science communication can be made to have a bigger impact on younger generations, especially because I feel like a lot of us are kind of like disillusioned by space now that it's almost like common with telecommunications, etc. And maybe by which means, if there's like new social media platforms or outlets you can think of, or maybe we need more role models, etc. So I was wondering what your thoughts were on this.
I think it's a really thanks Robin for the introduction. That's great. It's a really difficult question, that one, actually, because science communication comes at so many different levels. And like, I love going into schools, and I do a lot of schools talks, and there's a point where you think, oh, I'm only reaching maybe 100 kids, but actually those 100 kids will remember you. And I mean, genuinely, I walked past a playground the other day and a kid literally went, "Hey, are you the space lady?" Which I had to go, well, yeah, I suppose that is me. Yes, I did come and talk to you a while back. And they remembered it. And in fact, they then went on to talk about how the Chinese had landed on the moon and all this, because that had just happened. So it was like, they actually learned something and then come back to me. So I love that face-to-face ground level going into schools and enthusing kids. But to actually get people then to carry on into science, you've got to keep that going. And that's, I guess, where things like the National Science Centres, the Space Centre at Bristol or Techniquest in Cardiff, and there are lots around the country where you can go and follow up on that. But you've got the spark in the children so that they then have the enthusiasm to go. And it, making it, I guess, freely available is important as well. You can increase diversity and get everybody there. And yeah, there are so many aspects to science communication. I know there's some great YouTubers, but then how do you widen your YouTube audience? And I tweet a bit, but I don't put very much of my stuff out in the wider public domain, I suppose. And maybe I can do more. I don't know. I work at the moment. I've got a grant funded by the UK Space Agency. Actually, I'm working with some people at Cardiff University and the education sector here. I actually live in Cardiff, working here, where the Welsh curriculum is going to be changed. So we're going to integrate research on Insight straight into the secondary school curriculum for maths, science, IT. They're going to be learning all about Insight whilst learning to code in Python or learning how to read a graph, because they'll look at the pressure data from Mars from a, and it'll be the real data from the mission. There'll be access to that. So, there's different levels, I guess, of communication. So I don't have a golden answer, I'm afraid, but
that sounds great. Those are great. Those are great routes, really. I think changing curriculums in schools is definitely a major proponent, and actually changing curriculums in different countries as well. Because I come from a very French school background, and we have very little on engineering in general, and space is just never touched upon at all. I learned about space for the first time at university level, and for me, that's kind of a shame that not everyone has access. As you say, diversity and inclusivity has to be pushed with outreach societies, because I think it's a major problem, and it's the current limitation right now.
Yeah.
Okay, great. So we're going to move on to the talk now. I'm going to shut my camera, but please enjoy this talk by Anna, because I met Anna at the European Mars Conference actually last November, and I saw a very similar talk to this one, and it was completely breathtaking. So I hope you guys are ready for this. So Anna, here's to you.
Yeah, thank you. I'm just going to try and move you all off my screen. I hope that works. Okay. Oh. Nope, can't do that. Okay, let's just start, shall we? Right, so yeah, thanks, Robin. This is me talking about NASA's Insight mission to Mars. Robin's given you a pretty good introduction, so I'm just going to fly straight in with it. If I can progress the screen. There we go. Right. So one question I often get asked is why? Why do we keep going to Mars? And I'll be honest, I used to use a stock photo here of Mars because I think Mars is just utterly beautiful. But a couple of months ago, just before we went into lockdown, I was invited to a private viewing of Luke Jerram. I don't know whether anyone knows Luke Jerram, but he's this artist who did Gaia and the, what's it called, the University of the Moon. So and he spent an hour and a half just wandering around this globe looking at Mars. And anyone who could walk in that room and not just be totally bowled away by the idea of going to Mars and seeing Mars, I mean, you just have to not have a heart or a soul, really, to not be bowled away by it. So that's why we go, because Mars is just there and it's beautiful and we should go there. And which is why we've tried many, many times as a species. This is a little plot of the robotic missions that have been launched towards or attempted to get to the surface of Mars. And it's not always been a successful story. You'll notice a lot of the early missions had problems, either getting out of orbit or some of them missed the planet, which is harder, it's actually easier than you think to miss a planet. But recently we've had a lot of successful missions. I don't know whether you can see this clearly, but Mars Orbiter, we've got Maven, we've got obviously MSL, also known as Curiosity, and the satellites in orbit, like the Mars Reconnaissance Orbiter. So we've had lots of really, really successful missions. And in fact, this is Insight at the top because this has been updated. And of course, we've had rovers, landers on the planet itself. And thanks to these, we have the most amazing collection of images of Mars. I mean, I could literally spend days and days of my life just looking at images of Mars. So we know a lot about the outside of the planet. We know about the sand dunes. We know about the carbon dioxide ice that you see at the poles. We know about the rounded stones that Curiosity saw, which are obvious evidence of water. And we've even got images of outflow channels. I showed this to one of my kids and they went, it's a tadpole. And I went, no, it's a crater and an outflow channel where water has flown out of it. So we know a lot about the outside of the planet. And in fact, we've got the best topographical map of Mars of any planet in the solar system. So this is Mars. There are some really key features to notice here. First of all, let's have a look at the scale. This crater here is over 7 kilometers deep. It's a Hellas crater. These volcanoes over here, this is Olympus Mons. This is actually the largest known volcano in the solar system. This scale tops out at about 13 kilometers, 14 kilometers, but actually Olympus Mons goes up to 21. It's 3 times as high as Everest. This is just a huge volcano. And obviously we've got the Valles Marineris, huge canyon here, which just extends for thousands of kilometers. The other noticeable thing about Mars is that we have what we call the Martian dichotomy. So the southern hemisphere is heavily cratered and it's quite high topographically. So this is all above what the molar datum with the 0 point on the molar maps. And this is all high. And then the northern hemisphere is all quite young looking. There are very few craters. and is quite low down, topographically speaking. So what formed this, we're not entirely sure, but it's a very clear feature of the planet. So that's what the outside of Mars looks like. But for us, we want to know what's on the interior of Mars. That's what InSight is all about. So the key mission tagline is understand the formation and evolution of terrestrial planets through investigation of the interior structure and processes of Mars. And I'll talk a bit more about what exactly that means in a minute. And we've got three main techniques we're going to use. There's seismology, which is the key instrument, and then we have geodesy and heat flow, which leads us rather tenuously to an acronym even, interior exploration using seismic investigations, geodesy, and heat transport. And there's a reason we just call it InSight, because that's a real mouthful. So why do we want to go there? Well, really, we want to understand how terrestrial planets form. So I'm going to give you a quick view of how planets form, and then we'll talk more about Mars itself. So planets form when we have around a solar system, when the sun starts collapsing from the interstellar medium, from the dust cloud, then you get a protoplanetary disk around it of material. And this slowly, it accretes. And as you get accretion, you get a gravitational potential well, and things grow, and then they heat up as they're compacted. And that material that was relatively homogeneous, it melts, and then stuff happens. And eventually you end up with a planet, and you get differentiation of the planet, and you get a core and a mantle and a crust, and all of those layers are very different. And InSight wants to investigate the stuff happens bit. And the reason we have to go to Mars is because it's different from where we know about. So we've always wanted, so we know about Earth because of seismology. The only way to look inside a planet is seismology. If you think of seismology is like an MRI scan or an X-ray. We have energy sources, which are the earthquakes, and we have receivers, which are our seismometers, and the energy bounces through the planet. The waves travel, they are diffracted, reflected, all sorts of things by the layers they pass through, and then we record the signal on the other side, and we can reconstruct it to work out what was inside the planet, just like you do with an MRI scan. So it was obvious that when we started sending probes into space that we should send seismometers on them. So the moon landers, the Ranger landers, and the Apollo missions all took seismometers, some with greater and less success, but Apollo had them, and we have some great data from the moon, actually. And the first landers we sent to Mars carried seismometers, so Vikings 1 and 2 in the 1970s. That's this picture down here. I've lost the name. Here we go. This is Viking. And so, we knew this was the way to go. It just took us another 40 years to get it done. So I said we know a lot about Earth. Well, we've had over 100 years of terrestrial seismology on Earth. And also, obviously, we can go and explore it. We can look at the rocks. We can sample rocks from pretty much anywhere on Earth, even from the depths of the Marianas Trench. And the moon we know a fair bit about because, as I say, we took up the Apollo seismometers were deployed and ran for 8 years. And we also obviously brought back rock samples. So we've got a real idea of what the geology is, as well as the seismicity. So we know, for example, that the Earth is warm internally. It has a liquid outer core. It's got a nice dynamic magnetic field. And it's an active planet. We've got plate tectonics, volcanoes, and earthquakes. Whereas the moon is cold throughout. It's solid. There's a remnant of magnetism, but there's clearly nothing going on there anymore. And so it's very quiet now. There is some seismicity, but it's nothing like the seismicity on Earth. So most of the activity is historic and happened back in the past. So Mars is the middle ground. We know it was very active geologically. We have Olympus Mons, we have Valles Marineris, we have these huge geological features. But now it seems to have frozen. None of those things seem to be still active. And it appears to have effectively just had this boom where it's gone, right, here's all my heat, I'm going to throw all this stuff out, and then it's just cooled and contracted. And it's not quite as cold and dead as the moon, but it's certainly not Earth-like. So understanding what's going on Mars now might give us an indication of how planets have formed. Mars may have frozen at a point where it hasn't completely differentiated. So that would be very different from Earth, which has completely differentiated. So it gives us an idea of how planets form, how Earth might end up, and so we can learn a lot more about planetary formation. So InSight's mission science goals. So I'm just going to run over these quickly, and then we'll talk about the mission itself. So InSight's key goals, we want to understand, determine the size of the core. So how big is the core? What's it made of? Is it liquid? Is it solid? Is it partially differentiated? What is it like? Slightly molten. We want to know about the thickness and structure of the crust, and the same for the mantle. So again, are there distinct geological layers within, compositional layers within the mantle and the crust? And also, how warm is the planet? How much heat is actually still coming out of Mars? Is there enough for volcanism, that kind of thing? Or is it now just colder, so too cold inside? And we want to categorize the rate of seismicity and the rate of meteorite impacts, which again are really useful in aging planets. So how are we going to do all of this? Or how are we doing all of this now? Well, here's a schematic of insight. Now, I'm afraid there are a lot of acronyms. NASA, as you might guess, just by their own name, loves a good acronym. So I'm going to run you around this quickly, but don't worry if you don't remember everything. The only really important one is this one, and we'll get to that last. So IDS is the Instrument Deployment System. This is the robotic arm to you and me. And IDS actually has a grapple on the end and a scoop, and it has one of the two cameras. So this is the Instrument Deployment Camera, also known as IDC. We have a second camera here, which is the Instrument Context Camera, which has a view down, and that's the one you see a lot of photos from. We've got TWINS, which is the temperature for wind, temperature and wind for insight. And this is two wind booms on the deck of the lander. They point in opposite directions and they measure wind speed and direction. We've got RISE, which is the Rotation and Interior Structure Experiment, which is testing the reflexes of the planet in NASA speak. This is actually a really precise, it's almost like a GPS tracking system. It's actually a radio system, and it puts out, so we've got two radio antennae, they put out signals. We then record the time between those signals leaving the lander and reaching Earth, and the Doppler shift on those signals to give a precise location of where the lander is and therefore where Mars is, so that we can track the orbit of Mars to see how much it wobbles. And that will actually tell us about the structure and the size of the core, whether it's liquid, solid, and how big it is. So it's actually a really, really useful experiment. We've got HP cubed, which is also known as the MOLE. This is the Heat Flow and Physical Properties Probe, and that's obviously taking the temperature of the planet. The idea is that this will vary 5 meters down. I will touch on this very briefly later on, and it will measure the temperature as it goes. We've got the APSS, which is Auxiliary Payload Sensor Suite, which actually is a fancy word for saying lots of other sensors we thought might be useful and have turned out to actually be very useful. So there's a magnetometer and there's pressure sensors and temperature sensors. And then the golden boy of the whole project, SEIS, the Seismic Experiment for Interior Structure, and that in NASA speak is taking the pulse of Mars. And in fact, what you're looking at here is the wind and thermal shield, which is to keep it protected from the wind and the cold. And the seismometer itself is hidden underneath, but I'll show you that in more detail soon. And obviously, two major features of these solar panels on the side as well. So this is what the real spacecraft looked like, just to get an idea of scale. The solar panels, I think, about 3 meters across. These are obviously human beings for scale. And you can see here the wind and thermal shield, the MOLE here, the heat flow probes here. These silver cones are the RISE experiment. And this copper box is actually the seismometer. So that's what it looked like. And I'm going to talk to you a little bit here about the seismometer itself. This is quite exciting because it's actually 2 seismometers in one. So we've got what's called the VBB, or the Very Broad Band Seismometer. This was designed by the French team at CNES, and it's a bit like an Earth-based seismometer with a mass on a spring, a traditional force feedback mass. And there are those 3 of these, and they're all housed within this gold sphere, which is actually a vacuum chamber. And then this is the bit where Oxford really comes in, where we've got 3 short period sensors. These were designed by a team at Imperial College and built by Oxford and RAL Space. And then tested with some kinematrix electronics. So these were all built, they're basically put together in the UK, and they're tiny little things. So they come in this little block here. And actually this width here is about the diameter of a pound coin. So they're tiny little, they're etched from silicon wafers. And these are high frequency sensors. So SP stands for short period high frequency. And these are bolted on the side here. So we've got 3 of them around the outside. So it's a really great instrument because we've got the very broad band with the low frequency sensitivity, and then we've got the short period instruments with the high frequency sensitivity. So we've got a great seismometer. And in fact, I haven't told you this, the seismometer can measure vibrations on Mars that shake the ground less than the width of a hydrogen atom, which is just mind-blowing to me, that kind of precision of the minutiae that we can record. But what might we actually find? Well, what might cause quakes? So seismic sources on Mars, we've got a few little categories we could look at. So faults. This is an image of Mars, and you can see there's this nice bedrock layers running like this. And this one, obviously, there's a fault that runs right the way down here. And one of our team members, Martin Knapmeyer, mapped all the faults on Mars, or many of the faults on Mars, to show how they were either stretching or compressional faults, and some got normal faults and things. So there are plenty of faults on Mars, and you can see how they cluster with the tension or the compression. And here's Olympus Mons, and we're going to be over here with Insight. So there are definitely faults on Mars, so those could be moving. Phobos tide. Now, we're all used to the lunar tides. Obviously, here on Earth, we have a huge moon, and we have oceans, and the moon has a great effect on our planet. Mars has only got two very small moons, Phobos and Deimos, but Phobos transits quite close to Mars. So there is the potential for us to observe a tidal effect as Phobos passes overhead, which it does every few hours. It actually orbits very fast. Atmospheric excitation. Now, this to you and me is wind, basically. So this is a model of the current flow in the atmosphere. And although Mars's atmosphere is much, much thinner than that on Earth, it's like 1% that on Earth, it still has a great effect on the ground and on our seismometers. And we'll see some of that later in the talk. As Robin said, you will get to hear the wind on Mars. So it has a big effect. And we're learning an awful lot about the wind, actually, from this mission. And also meteorite impacts. These are a couple of images taken by, I think it was Highrise. Here, there's nothing. Here you see this great big black puff of dust. Basically, the oxidized red crust of Mars, the dust of Mars, is blown out by the meteorite impact. And meteorite impacts are really cool. If we can see the seismic signal from meteorite impact, then it's like a calibration shot. You know, a lot of our models here on Earth of seismicity are based on results of recording seismic signals from bombs or nuclear explosions, nuclear tests, things like that, because you have a precise size of event in a known location. And with that, you can then calibrate all your models. So for us, if we could get an image of a meteorite impact and then see the seismic signal from it, then we could calibrate all our velocity models. So we're really looking out for a meteorite impact. If we saw one like this, that would be great. So how are we going to make all this work, though? How are we going to do the science? Well, the mission has two primary output services. We have a huge science team. There are like 150 of us working on the science team, but we got these two output services that help everybody else get on with stuff, I guess. So MQS, the MarsQuake Service, the team I work for, and MSS, the Mars Structure Service. So MQS, our job is to detect and locate Marsquakes and produce a catalogue of the seismicity. So we have a frontline team of 10 of us who take shifts. We're on duty for a couple of days at a time, and we look at the data as soon as it comes down, just like a kind of earthbound seismic service would. And then we look for quakes and we catalogue them, and we tell the rest of the team about them, and we do actually release the catalogue and the data publicly as well, so everyone else can look at the data too. And then from those quakes, the Mars Structure Service use the locations and the phases we've found, and then they invert that for the internal structure of the planet. So that's how we're going to find out about Mars. So what's the reality? That was, of course, was the plan. The reality, well, do you know what? I joined this mission in April 2018, and we launched on May 5th, 2018. And I was so excited when I got my invite from NASA to come out to the Vandenberg Air Base, to come out to the US and watch the launch. And we all got given these little VIP guest lanyards, and we got on a bus at 2 in the morning, and they drove us to a field. And thankfully in the field, they put up these TV screens, because it was so foggy. I mean, look, you can see here, this is the closest camera they can get, and you can still hardly see the rocket. So I did have a video of the actual launch, and it includes a foggy field in which you can see nothing, and a rumble. You can hear it. You can hear it. It was an amazing experience. I'm making it sound like it's rubbish. It wasn't rubbish. It was super exciting, but couldn't actually see anything from where we were except for on this screen. Cory Houston, on the other hand, who works for NASA, went up on the hills above LA and took this photo as Insight came out of the fog bank that lies over the west coast of America. And yeah, we had proof that Insight really was on its way. And wow, that was some day. But where is it going? Well, the landing site, choosing a landing site is a tricky business. we were coming into Mars via parachute. So we're obviously flown all the way there. There were no orbiting maneuvers or anything like that. It was just, there's Mars, we're coming for you, straight in. And that there was a very scary video released actually just a couple of weeks before landing that NASA put out. You should go and look it up actually if you haven't seen it yet, because absolutely terrifying to see 2 weeks before landing, about the G-forces, the heat that it goes through on the way in. One of the important things is slowing down your spacecraft. So you want to get your spacecraft to as low an altitude as possible, and have it so you have as much atmosphere as possible, because we were slowing down with a parachute. So we wanted to be, this is in the northern hemisphere, so that we were in somewhere lower. There's the red, if you remember, red and white high, and green and blue are low altitudes. So we wanted to be low down. Secondly, you need to be able to power your spacecraft when you get there. Well, our spacecraft is powered by solar panels, so we need to be near the equator. So the equator is here, and you'll notice that Opportunity was just below the equator. Spirit wasn't too far below. Curiosity is close as well, although that doesn't need solar power. And yeah, Phoenix. If anyone's wondering why would you put Phoenix up there, that was going to the North Pole, so it had to go there. But generally, you try to keep them close to the equator. Thirdly, for InSight, we needed somewhere flat, and we've got 3 legs. If we hit a rock, we fall over. We've got a 15 meter, no, not 5 meter span, I think we are. So if the solar panels can't open to the sides, if they hit a rock, if we're at more than a 15-degree tilt, the whole spacecraft is a little bit in trouble, really, with power. So that's why we chose where we went, and it also was a useful place, kind of geologically speaking. So the target was Elysium Planitia. So here's InSight, here's Curiosity and Gale Crater. So Elysium Planitia is here. Elysium Mons is another ancient volcano. And yeah, we are here north of the Martian hemispheric dichotomy. So I mentioned that earlier. And Cerberus Fossae is here. Remember that name because it will come up later. This is an area, it's only 1,500 kilometers away from us approximately, and it's got faults, and it's got volcanic flows, and it's got evidence of liquid water outflow channels that we can date to being within 2 to 10 million years. That may sound like a long time to you, but geologically speaking, that's not long ago. So that's where we were going. And if we get a close-up of this, that's my laser pointer, sorry. Some poor PhD students got to spend a very long time counting rocks from images like this, and craters and topography levels. So you can see there's kind of faults, there's ridges, there's craters. There are each of these little pot marks is a crater. And they had higher resolution images, so they could literally count the rocks to try and choose the best landing ellipse. And this was the landing ellipse chosen for us. Now, one little fact about this is that to hit that landing ellipse from Earth is like me sitting here in the UK throwing a baseball to my sister who lives in Philadelphia. And I'm not only going to throw the baseball and have it get to Philadelphia. I'm throwing a baseball, obviously, so that she knows what it is when she catches it. It's not going to be a tennis ball or anything, baseball. So I'm throwing that off to Philadelphia, but not just to Philadelphia, not just to her house, but to her full stop key on her laptop, in her study, in her house in Philadelphia. That is the precision that's required to get a spacecraft just to within that ellipse. So just kind of keep that in mind as I show you this. The red dot is where we landed, which it still blows my mind, really, that they managed to hit the target so well. So there we were on Mars, and literally within minutes, we had this image of Mars. Now, a lot of people said, God, it's really dusty. They're like, yeah, we just fired retro rockets into a dusty planet, and that camera is on the bottom of the spacecraft. So yes, there's dust on our lens cap, and it is a lens cap. What actually was more terrifying, or more, I don't know what the word is, kind of comforting, I suppose. This here is the foot of our lander. This is a rock. And there's a great story about our PI here, Tom Pike, who designed the short period instrument. He's at Imperial College, and he spoke to one of his students or his postdocs earlier that day. On landing day, they'd been told that there was a 1 in 52 chance of hitting a rock on landing. And Tom said to Konstantinos, here's my deck of cards. If you pick the ace of spades, then, that's the same as us hitting a rock. So which, of course, Konstantinos picked the ace of spades. So within the team, this is the ace of spades rock. And yeah, we just missed it, thankfully. Otherwise, that could have been mission over, quite literally. Now, what's one of those little things that I love about this mission is that we got that image within minutes. I was hosting a landing event in Oxford University actually at the time, and we'd heard the live feed, and everyone else had gone out to get a drink, and then we got that image back in, and it was like, we've got this image, like literally within minutes. The reason we got that image was these two chaps here. These are Marco A and B, also known as Wally and Eva. After the film Wall-E. If you haven't seen it, go watch it. You'll know what I'm talking about. These are what we call Suitcase Satellites, and they are just tiny little box, Mars Cube 1s, these ones are called, and you see how small they are, literally, and this is a normal person, tiny little things, but these were launched alongside InSight. They flew along behind InSight, just so that as InSight entered the Martian atmosphere, they could pick up the signals as InSight landed and relay them back to us, because none of the orbiting satellites were going to be in range. So we would have had to wait for the orbiting satellites to then touch base with InSight and send us back the images. As it was, the Marcos took the images and sent them back to us. And they did a fantastic job. And I would have to say I was very sad when 4 months later we heard that we'd heard the last of them, quite literally, because they were set on a trajectory to fly by Mars and then just carry on, and they're out there somewhere. But it was the first time we've sent CubeSats out into space rather than just in low Earth orbit like we normally do. So they're a real trailblazer. I'm sure they'll be used on many more missions in the future. So thank you, Marco A and B. So we were there, and the next morning we got this image. So this is from the instrument deployment camera. So this is the one I just tried to point at the screen. That doesn't help. Here, this is on the robotic arm. You can see our grapple here that we'll use later to deploy the instruments, and here's the scoop. And there is Mars, and here's our seismometer, and you can see its nice little suspension legs so that we can adjust the height. And just getting these images was fascinating, but there's actually so much detail in them. For example, here, there's a huge rock, which we nicknamed Dwayne the Rock, after Dwayne Johnson the Rock, obviously. We're not very original with names, but that was a huge rock. If we'd hit that, would have been in big trouble. And actually, if you look out across this vista in front of us, you can see that we were really lucky. We arrived in what's known as a degraded crater. So obviously it was an impact crater, but now it's full of dust. And you can see it's quite smooth. And you can see other ones of these in the distance. So there's one here and there's one here. But when you're not in one of these degraded craters, you're in quite a rocky terrain, in fact. And if we'd landed outside of the crater on this, we could have been in trouble. So yeah, really lucky with where we landed. And to make sure we knew exactly where we were, we sent a Highrise, which is another one of NASA's cameras, up to take on the reconnaissance orbiter to take photos for us. And nothing is green. The green is saturation of camera. The camera is designed to look at red planets, not bright reflective shields. So first up here, the lander is this here. We know this is the lander. We can see both solar panels are deployed, the black lobes on the side, and the very bright green bit is the wind and thermal shield for the seismometer, that white dome you saw. And you can see the dust that we kicked up with the retro thrusters, and you can also see the prevailing wind direction from the fact that there's a streak of dust going back this way. Here, we've got the heat shield, which landed on the edge of a crater. That would have been a really rubbish place for us to land the InSight. So that's here. And down here, you can see the parachute. And actually, if you zoom in, you can actually see the parachute, again, showing the prevailing wind. So the back shell hit the ground and the parachute blew off to the southwest. So yeah, we've left a bit of debris on Mars, but InSight landed in the best place it could, really, given what we were looking at. So we're there. But here's the critical point. Here's the seismometer, and here's the ground. Now, we've done this before with the Viking experiments. We sent seismometers to Mars, but if you send a seismometer planet, and what you want to measure is the ground, but the thing you're on has shock absorbers in its legs, that's these, then you don't really hear a lot of the ground, and you do hear a lot of the wind. So we wanted to see what the wind was like where we landed. So we turned on the short period instruments while we were on deck, while the seismometer was still on the deck, within the first day or two of being on Mars. So hopefully this will work. I'm going to press play, and hopefully you can hear the sound of the wind on Mars. Now, if you can't hear it, come back and listen to this another day with headphones on. It's beautiful noise, and you can also pick it up off the NASA website as well. And every time I listen to it, I was like, it's just wind. But it's the wind on Mars, and it's basically we picked up the vibrations of the solar panels that then shook the lander, which shook our seismometer. And it wouldn't have been audible, but we've scaled it up 2 octaves to make it in the audible range. So that's the wind on Mars. But of course, we didn't go there to look at the wind on Mars. We went there to look at the seismicity of Mars. So deploying the seismometer. Now, deployment on Earth, this is me deploying a seismometer in Canada. So this is the seismometer. You dig a hole, you protect the seismometer with some plastic bags or a barrel, whatever you've got really. You bury the seismometer, you check it all works with the computer, you make sure it's got power, and then you leave it alone. And that can take, anything from an hour to 2 or 3 hours, depending on how elaborate you make your solar panel stand, basically. And it's a really quick process. But on Mars, it took us 70 days to get the seismometer happily on the ground. And that's partly because we had to take photos of all the ground that we could reach in front of the lander. And then we had to choose the best places. We had 2 instruments to put on the ground. And then there were lots of things we had to do. So this is a little GIF that NASA made actually. It's like their first 100 days. So I'll try and talk through it, but without talking too much over it. So here you go. This is the first image. And there's the Ace of Spades rock. And here's the GIF. You'll see the dust gets blown off by the wind. The robotic arm has a good check about. And then we decide on Sol 22, we put the seismometer on the ground. But then there was a lot still to do. So we didn't let go of it until Sol 25. Sol is a Martian day, by the way. And then we had to drop this cable. And then we have a very elaborate thing here called the load shunt adjuster to stop vibrations from the cable going straight into the seismometer. We put in a loop of cable, but we needed to open that loop by tugging. You can see there's this little peg here. We tried to get with the grapple to pull this cable back to open that. And you'll see this does spring open. But that took us a lot longer than we thought it would. So that took 2 or 3 weeks of very careful work from the engineering team. There's the wind and thermal shield. The temperature difference on the surface of Mars is like 100 degrees every day. And the average is minus 50 degrees. So it goes from about 0 to minus 100 every day. And seismometers don't really like that. So we try to protect it as much as possible. This here is HP cubed being deployed on the ground, the MOL, the heat flow probe. That's its housing. And in fact, you'll see that jump about in a minute when it starts hammering. There it goes. And we also, I don't know whether we've had those yet, the Phobos eclipse. You might have seen a very brief darkening there, and we imaged sunset and sunrise as we came up to the equinox. So that's where we were at day 100. So it had taken 70 days to get the seismometer to the point we really wanted it on Mars. But at that point, it was properly deployed. What you'll notice now also is this image is much, much clearer than when we started. It's because the wind has turned around and it's blown dust off the camera, which is useful. So there we go, seismometers on Mars. So what are we seeing? This is the kind of thing I look at a lot of the time. Every day I look at things like this. This is a spectrogram of the seismic signal from one Martian day. So you'll notice we've got date in UTC here, so this is Earth days, and then we've got it in Martian local solar time. So this is the Sol is the Martian day since we landed on the planet. So we look at these plots basically from midnight to midnight for each Martian day. What you've got is that this is the paraspectral density, so this is kind of the amplitude of the signal effectively for each different frequency. What you'll notice, so yellow is strongest signal. We have this very noisy patch in the middle of the day. This is the winds, where basically when the temperature rises, the wind blows, and we obviously pick up that atmospheric excitation on the lander. In the evening after sunset, which sunset goes about here, it gets much, much quieter and you get all this dark blue patches. There are a few other key features. You'll see these vertical spikes down here that you see. These are glitches. Now, all seismic instruments have glitches. It's just basically where the instrument kind of cracks or pops, maybe thermal, maybe tilt-based, all sorts of reasons. We don't see them so much on Earth because there's so much other noise going on Earth. But on Mars, the noise in these quiet periods here is like 500 times lower than the seismic noise on Earth because there's no oceans and there's no trees and there's no people. So it's really quiet. Other key features you've got these horizontal bands you can see, or this one's not particularly horizontal because it has a dip, but this one's temperature dependent. These bands here are lander modes. So those are the frequencies a lander vibrates at. And you can tell that when the wind drops, they drop. So the lander stops shaking. This other mode we have here, this is 2.4 hertz mode. This is a bit enigmatic. To be honest, none of us is quite sure exactly what's causing this yet. It may be the planet itself, maybe something about the geology exactly under where we are. It may be something else to do with the lander. And also here we've got actually 2 Marsquakes on this day. These particular bursts of energy are Marsquakes. They're different from the wind. They don't cover all frequencies. They just cover some frequencies. And they occur, particularly here, they've occurred in the quiet time, which is why we can detect them. So we'll talk a bit more about those as I go through. So we plot each one of these. This is a plot of, each one of these is one of those daily spectrograms, and you're going from when we put the seismometer on the ground to, this is about Sol 300. This is the data we've published in this format. We've actually now got to Sol 530, but I wasn't allowed to show you all the latest things. But you can see how the weather has evolved. So when we first arrived, there was a lot of diffuse wind. It happened a lot all day long, but it was quite variable. Then we had this patch where we had very high winds in the middle of the day. The white band here, this is solar conjunction. So Mars went the opposite side of the sun and we couldn't communicate with the lander, so we don't have any data there. And then we came back after solar conjunction and similarly, similar noise pattern. And here are the quakes that we recorded at this point. And we divide our quakes into what we call low frequency family of events and the high frequency family of events. Basically, those are ones that have frequencies dominantly below 2.4 hertz and frequencies dominantly above, like 2.4 hertz or above. So that's what the low frequency and the high frequency families are. And they're very distinct kind of quakes. So let's talk about the quakes. Sol 128, this is the first quake we went public with, and this is the spectrogram for Sol 128. You can see the kind of noisy day period. There was some noise in the morning. There was a little bit noisier in the evening that day. And the Marsquake itself is here. It's a bit hard to spot. This is a high frequency quake. Now, if we go to the next slide, hopefully you can hear it. So what you're going to hear with this sound file is you're going to hear some wind, then you're going to hear the Marsquake, then you're going to hear the movement of the robotic arm, which is just the coolest noise. So let me play it to you. That's wind. No more wind. There's lots of wind on Mars. And that was the Marsquake. And then there's some more wind. And here comes the robotic arm. And a couple of adjustments to the arm. So when people say to me, oh, well, how do you know whether it's a quake or wind? Well, not only the waveform's different, but the sounds are very different as well. I think you could probably hear that. They're very clearly different kind of signal. So I remember first hearing that and going, oh my God, listen to it. And also, doesn't it sound a bit like a tube train? You know, like that kind of rush of it. Anyway, I'll move on. Marsquakes, really cool. So that was a high frequency one. This is a low frequency quake. Again, I don't know whether you can spot it. Here's the, I've lost my cursor. Lost it, here it is. Here's the noisy bit in the middle. Here's your quiet evening. And the Marsquake is here. Now, there is a sound file to go with this one, but I'm not going to play it today because it doesn't come out well unless you're sat at home with really good noise cancelling headphones with lots of bass in. So go look it up. It's there's a link here, but if you just go search, Sounds of Insight or something, you'll find it as well through Google. But it has a very different tone to the last one you heard because it is much lower frequency. And even though all of them have had to be amplitude and frequency, it still sounds very different. So what's interesting about that last quake, that low frequency one, the 173, it happened on Sol 173, so it's called S0173A, that's our numbering scheme for quakes, is that it has two really clear phases. So those are our typical earthquake phases, the primary compressional wave and the S shear wave. Now, these, what's really cool about this particular event is that we also had polarization on those phases. So if you've got two phases, then if you've got a velocity model, you know that a P wave moves like this and an S wave moves like that. They travel at different speeds through the material, so you can work out how far away the quake was. So that's all well and good. But we also wanted to know where it came from. Now, with this particular quake, we could get polarization, so we could track the particle motion from the waveforms, which could tell us which way the wave came from. And from that, we could track that quake to here. This is a kind of ellipse of probability of where it was, and also a second quake, a low frequency one, S0235B, which also has beautiful polarization, and that tracks to here. And both of these intersect Cerberus fossae. So I told you to remember that. This is an area, these faults are over 1,000 kilometers long. They're kind of dikes in the ground. They're huge features, and they're young, only like 2 to 10 million years. And we are seeing what we think are at least a couple of quakes that come from that region, which represents that there may not be kind of the geological activity that formed those faults still going on, but there is definitely still stress there. We've got satellite images of rock falls happening inside these faults. And the size of the boulders falling are too big just to be wind-blown pebbles. These are rocks that have obviously been shaken. So we know something's going on in Cerberus fossae, and now we've got 2 quakes that we can see happening there. So, and there's a third quake relocated to over here as well. So this was a really, really exciting result for us. And this is what Cerberus fossae looks like, these long trenches that you see, and they're very narrow trenches. And you see they cut across other geological features, which is how we know they're relatively young. So earthquakes, moonquakes, and Marsquakes. So the Marsquakes are quite different from earthquakes. And what I showed you there, that was one of the low frequency ones. And we also have the high frequency ones, which are much more, I think you saw it, you heard the sound of it. It's more homogeneous in its waveform. It's very scattered signal. So an earthquake, this is a local earthquake to our team in Zurich, who run head up the MarsQuake service for us. This is a typical local earthquake that you'd get in Switzerland, so it lasts about 30 seconds. And then this is a quake that they recorded in Switzerland, but actually happened in the North Atlantic at 2,500 kilometers away. And the main arrival phase is like 5 minutes long. Our Marsquake recorded at 1,500 kilometers. This is the 173 event we've just been looking at. It takes about 15 minutes, and it's got a very scattered signal. A moonquake, these can last more than an hour. The moon is so dry and scattering that the wave just basically bounces about all over the place. You can't tell where it came from. And it seems to come from all sorts of different directions. And it keeps ringing and vibrating because things have just taken different paths to get to you. So moonquakes are really hard to work out what's going on. Marsquakes are a little bit easier. And we've got some ideas about what we're seeing. So with our 2 different kinds of quakes, the low frequency ones and the high frequency ones, we think that the low frequency ones are located kind of in the mantle, and their waves propagate in the mantle, and they have the high frequency content of them is attenuated by the mantle. And there might even be a low velocity layer somewhere within the mantle. So we might be getting an idea about the actual structure of the mantle. On the other side of the map, we've got the high frequency events, a bit like the 1281, and we have hundreds more of that kind of an event. And these we think may be crustal events, possibly, where the signal is just trapped in the crust and bouncing about, and crust acts like a waveguide. We're still looking into this, but that's our first theory on them. So we are really starting to learn about the structure of the planet. Now, I couldn't end a talk without talking about the mole, the heat flow probe. Everybody always wants to know what's going on with the mole. So the mole is a self-propelling probe. Basically, it's the probe, and inside the probe, there's a mass on a spring, and the mass is wound up by the motor and then dropped. So it hits the bottom of the probe and should force it down. Of course, there's a bit of recoil, so that bounces back a little bit. But the idea was that it would hammer its way 5 meters down. 5 meters is the depth that planetary protection law said we'd have to stop at, but 5 meters would be enough to get an idea of the temperature profile of the planet. You can extrapolate from that kind of depth. So it was going to be really, really useful. Unfortunately, it progressed a little bit and then it got stuck. And then we took the housing off so that we could see what was going on, and then it progressed a bit and then it bounced out again, and then it progressed a bit and it bounced out. And anyway, it was a bit of an up and down story, moles popping out of holes. And now we've been pressing with the scoop. So this scoop on the arm wasn't really designed to push on things, and we said we'd never push on the back of the mole, but because this cable is the science tether, this tether is actually instrumented all the way with heat sensors, so we can't damage the tether. But very delicately, the operations team have done an amazing job recently, and they are just gently, they lifted the scoop today so they could look at it, and then they put the scoop back down again. These were, Saturday. And so they are pushing very gently on the scoop, and then they'll hammer a few times and see if it progresses on downwards. And fingers crossed it will go. It is getting further down, and we'll just have to watch this space. We're going to hammer again on, what day are we on now? On Friday. So on Friday, there'll be new images and we'll be able to see whether it's gone any further. So hopefully we'll keep going down. So that's where the mole is, if anyone needs to know. So a quick mission update on Sol 531. The lander is green, so all systems are operating nominally, despite the fact that we're in a global pandemic and we've all been locked down and all of that kind of thing. Data's still flowing. Obviously, InSight's been in isolation for 500 days, so she's fine. But we've taken 4,613 images as of this morning. They're all available on the website. You just go and have a look. Really, you can just, again, lose days. They get a little bit tedious after a while. We've seen over 500 signals with potential seismic origin, and about 40 of those are strongly considered to be quakes. Those are 40 which are in that low frequency family, we think are like probably mantle quakes. The other, 400 odd could well be quakes, crustal quakes. We just want to find out a little bit more about them before we say too much on those. And two of our quakes, as I say, we've located to Cerberus Fossae, which is an area of geologically recent faulting. So that's really cool. So Mars is definitely quaking. And on that note, I'm going to leave you with my Twitter handle and the website. And we can bring Robin back, who's probably got questions for me. And hopefully you have. So I hope you've enjoyed this. Thanks, everyone.
Yeah! Thank you. I'm clapping on behalf of everyone on YouTube right now and everyone online. Thank you, Anna. That was amazing. I mean, I've learned new things as well, despite having seen this talk before. It's honestly, you're such a great science communication presenter as well, and you're a great scientist as well. So I think the combination is just like a killer opportunity for everyone watching to learn about this in a very compact and precise way. So we're going to move on to like a really quick Q&A. If you have more questions, please feel free to send them on YouTube right now or on Twitter at AerOx_space. So first question, just from my part, really, really simple, related to the talk. You mentioned that some of the meteorites are used as calibration on the surface. And I was just wondering if like the dust on Mars remove those calibration patterns at some point, and how long does that usually take? Like how long are those calibration points reliable for?
Yeah, that's a really good question, actually. And we've been trying to work out exactly how long it takes for the dust to get blown away, because obviously the craters do get blown away, like you said. It's also really hard because we only get images of certain areas. You can't be watching the whole planet all the time in high resolution. Yeah. But we are, so I can't really answer the question exactly how long it will be, or how long they last, but we are really hoping that we can see something. We haven't seen anything yet. Okay. That we can see seismically. We can say that's definitely a meteorite impact. It's really difficult because on Earth, even on Earth actually, determining an explosion from a quake is kind of tricky. But obviously on Earth we've got many more seismometers, so you've got a better chance of pinpointing it and looking at the explosive nature of the impact or the explosion as it is on Earth. But yeah, that's a really good question. Hopefully not before we see them.
Great. Thank you for that. Chris, who is the co-president of Aeronautical Society, also currently online, for you guys who all know, is asking, which experiment would you hope for if you could choose any to go in the next mission, on the next Mars mission, on the next Martian probe? And would your answer change if if we had the certainty that humans were to go to Mars? So would that experiment change?
Oh gosh.
That's quite broad.
That's a really difficult one. Obviously, I'm totally biased, and I'd really like another seismometer. So that would be, but that might be a bolt-on. It would. I'd like to get further into the crust and find out what's down. I mean, obviously the mole might get 5 meters, but all the other landers, like Curiosity and whatever, they've been able to scrape or drill a very short way into the ground. They literally like scrape the surface and actually be able to drill down, because if there is water down there or water, ice or everything, that's where life or whatever might be. So that's obviously, you don't want to contaminate it, but you want to, if you're going to send humans there, then we need to know if there's anything else there first, because we don't want to kill off or whatever, or be killed off. So I guess that would be on the hunt for life.
Yeah, there's a few questions regarding Hunt for Life after that. Obviously, I think everyone's really interested in that. Patrick from Mars Society UK is asking if you think InSight will offer any clues as to the origin of the Martian dichotomies. Do you think that's possible?
Possibly. I mean, if we can maybe not. Well, I suppose if we can work out the internal structure, if we can work out the structural differences, if we could pinpoint enough quakes to be coming from the north and enough from the south to get different velocity models from those two regions, then that would give us an idea of the structure, and from that we could infer what caused it. So maybe it will depend on us seeing many more bigger quakes than we have so far.
Great.
But fingers crossed.
Thank you. And actually another question from Pat as well. He says, apart from the wind, are there other alternative origins to the signals, do you think? And actually, I was curious about that as well. Do you think it's something else in the wind, or is it 100% you're sure it's the wind, like the background noises on the signals?
I think what we've seen so far is that the background noise is almost certainly it's wind and pressure changes, because we've got the wind sensors and we've got the pressure sensors. So one thing I didn't show you today because I didn't have time was signals from dust devils. So for example,
I remember that.
Yeah. A dust devil is like a mini tornado. It's like a little vortex, convective vortex, and they pick up dust, and they have a low pressure point in the middle, and you see that on you see a pressure drop on the pressure sensor, but you also see the seismic signal. Literally, you see a spike in the seismic signal, and there's I don't know what else then you'd be hoping we were going to be seeing, like Martians. I don't know.
I guess like during the day, during the daytime when the signals are really, really high frequency and really high intensity, do you think that there's something else? Is there a pattern of like, oh, this is definitely only just the wind? And
well, we're certainly seeing now. So I couldn't show you the latest data, the latest spectrogram plot, but that plot you can see the seasons changing. So we know, like we can see the wind changing. There's a great plot actually in one of our Nature papers where you can see the wind and the pressure and the seismic signal, and basically they do the same.
They're clear.
Yeah.
Great. I'm glad you're clear on this. Thank you for that. We have a question from Ty Yamnitz. I hope I pronounced that right. If Mars has quakes, then does that mean it's technically not a dead planet?
Ooh.
Some pointed questions for you, Anna.
That's an important question. Well, the way we think most of the quakes are forming is from cooling and contracting of the planet. So just like, I think I used this analogy with Chris one time with Chris Lintott, is if you've got a cake and you take it out of the oven and it's nicely puffed up, and then it cools down and it shrinks and you get all those crinkly lines on the top, and that's all that contraction going on. The planet is contracting as it cools, so you're getting stress release at the surface. Whether that stress is released all the way through or is just in certain regions, that's still up for debate, but we at the moment we still think that that's most of the theory. We are looking at the ideas of maybe some of the quakes could be tremor induced, like from underground lava, but we don't have any proof of that yet. So we are investigating things. So is it dead? It's more dead than Earth, that's for sure.
But, quote of the talk.
Oh God, that's going to come back to haunt me, isn't it?
No, thank you for that.
Yeah, we will see. If we see a really big one, then we'll have to kind of go,
And that's in question. Thank you for that. I have a question regarding, it's a very quick one. I was wondering if any astrobiologists were involved in the InSight mission, or if they were involved in other missions, or if you guys collaborate between seismologists. Is there some kind of collaborative effort? People trying to find more organic things? Yeah,
I don't know of many involved in InSight. I may be wrong. I say I've joined it very much as a seismologist. Obviously, the Rosalind Franklin rover, which unfortunately its launch has been delayed by 2 years, but that is going to look for life. So that's doing that. We're a bunch of physicists basically on our mission.
Okay, that's good to know. Chris is asking if the seismic activity of Mars is any indication. Oh, I guess I kind of asked that if it's any indication of whether life ever existed on Mars. But I guess you've kind of answered that through the previous question. So I'm just gonna
life and the planet being geologically active, maybe two very different things. The planet could be geologically active, but it still might not have life in a biological sense.
but actually he has a more important question of, do you think the rise of the current commercial spaceflight here on Earth will change the nature of the scientific experiments being sent to space and might affect future missions, like missions to Mars? Do you think that's a possibility? It's quite broad.
Probably. I think, at the moment, like this mission, I know this one was a long time in the planning, but we were very much, this is a very science mission. This is very much kind of, we're going there to find out about the planet, just so that we can find out about the planet, so that we can learn about how other planets might form. We're not really going there to find out whether it would be a nice habitable place. We know that it's not. It's really cold. It's got no oxygen. Yeah. Who wants to go there? But I think commercial flight, well, they're, why are they doing it? They're going there to they're either going there to inhabit them. So you got to look for minerals, you got to look for, ways to sustain life. So I think it will change it. Almost certainly, because the ulterior motive is different. That's not to say that all commercial entities are all simply about making money and colonizing other planets, but they're probably more, that's probably where the money is, rather than just, how do planets form? It's just like kind of, so I think it will have an impact. Whether that is 100% detrimental is, probably not. It's probably quite useful stuff to know, but I just hope we don't end up with too much space junk.
I was gonna mention space debris, and
I feel really bad when I look at the images of Mars and it's like, we just left some shit about, they're over there, over there, we're just gonna leave it there.
Great. And then one final question before we wrap up. It's already 6. One question from Christina. She says, you showed Mars as lying in between Earth and the Moon in terms of activity. Has the science shown anything that's unexpected? Have we learned anything surprising in this respect?
No. I mean, we went there with pretty broad models. We were like, Moon, Earth, we're going to be like this much between space. So we set our boundaries quite wide. And in that sense, what we're at is kind of where we thought we would be. I suppose one thing we found is that all our quakes, so on Earth, you've got a pretty good distribution of different sizes of quakes. So you get more, obviously, the smaller quakes and fewer of the bigger ones, but we're actually seeing a real cutoff in this rate. So we haven't seen anything above a magnitude 4. So obviously the seismicity on Mars is very different from Earth, and we obviously don't have plate tectonics, so we don't have the major driving force for seismicity on Earth. But there is a difference in what we might have expected the rate of seismicity to be. So we're not seeing, there's a lack of big quakes. So that's one thing that it is different. But that's not necessarily something we didn't expect. It's just something that we've seen. So yeah, nothing major that we hadn't predicted. The atmospheric scientists are having a great time though. They are learning so much about atmospheric models that will have a huge impact on our future missions to other planets as well, I think, because the way they model planetary circulation, atmospheric circulation, is definitely changing from what they're learning from InSight. So that's been a real bonus. Yeah.
Great. So everyone go into atmospheric physics. You heard it from Anna. Thank you so much, Anna. We're going to wrap up. So I just wanted to obviously thank you for such an insightful and really enjoyable light talk. I truly can't get bored of these kind of talks at all. And I definitely do think the world needs more of you in terms of trying to inspire more people to get into aerospace, because it's really rare to come across people like you, I think. Thank you to Lucinda from the Mars Study UK for introducing me to Anna and organizing the European Mars Conference, which led to this. And obviously a massive thank you to Chris, who was behind the scenes for the whole run through and has been dealing with all the tech. So, and thank you for joining and tuning in. If you still have questions, you can still tweet us. And again, if you'd like to join us as well, please feel free to email us. We're welcoming 80 students to get involved. But yeah, thank you, Anna, and thank you for joining us.
Thank you.